Hi, good morning, afternoon, or night, depending in the time what you see this video. My team is conformed by Sergio Rafael Delgado Luna, Ulises Alejandro Soto Martinez, and me, Ulises Jared Perez Andrade. We talk about two types of controllers, and we start. And the first controller is the on-off, and the final control element is either on-off on or off one for the occasion when the value of the measured variable is above the set point, and the other for the occasion when the value is below the set point. The controller will never keep the final control element in an immediate position. Controlling activity is achieved by the period on-off cycling action. In the figure in the slide number 3, we have a tank. It's a system using on-off control in which a liquid is heated by steam, and the operation of the process can be summarized as follows. First, if the liquid temperature goes below the set point, the steam valve opens and the steam is turned on. And when the liquid temperature goes above the set point, uh, the steam valve closes and the steam is shut off. And the on-off cycle will continue as long as the system is operating. Well, and then next slide and next controller is the proportional controller. These are designed to eliminate the hearing or cycling associated with on-off control. They allow the final control element to take in intermediate position between on and off. Proportioning action permits analog control of the final control element to vary amount to the process, depending on how much the value of the measured variable has shifted from the desired value. A proportional controller allows tighter control of the process variable because its output can take on any value between on fully and fully off, and depending on the magnitude to the error signal. And now we have an example explained by my classmate Soto Martinez.
An example of control provides these values that is controlled by a current. To 4 milliamperes, the answer is 0, and then begins to increase varying 2 milliamperes to 12.5% to 100%. Proportionate action can also be accomplished by turning the final control element on off for the short intervals. This time proportionating, also known as a pulse width modulation, varies the radio off on a time to off. And actions. Proportional control is often used in a conjunction with integral control or derivative control. The integral action, sometimes termed reset action, responds to the size and time duration of the error signal. An error signal exists when there is a difference between the process variable and the set point. The derivative action responds to the speed at which the error signal is changed. That is, the greater error change, the greater correction outputs. The derivative action is measured in the terms of time. Pi and Pd. Proportional plus integral Pi controls combine the characteristics of both types of control. A step change in the set point causes the controller response proportionally, followed by the integral response, which is added to proportional response. Because the integral mode determines output change as a function of the time. The more integral action found in the control, the faster the output change. Proportional plus derivative PD control is used in process control system with errors that change very rapidly. By adding derivative control to proportional control, we obtain controller outputs that respond to the error rates change as well to its magnitude.
Hello, my name is Sergio Delgado. I'm going to talk to you about the PID control. The PID control is a feedback control method that combines proportional control, that's why it's the P, integral control, that's why it's the I, and derivative control, that's why it's the D. That's why we call it PID. This type of control makes the smoothest and quickest control response without hunting. Hunting is when the response is trying to settle into the set point and make curves. That curves get thinner and thinner and thinner until it reaches the set point and it stabilizes. With this type of control, we reach the set point as much as possible. We avoid the hunting as much as it can. So the response, instead of being something like this, we try to make it just the less curves as possible and get to stabilize into the set point. This type of control is most used because of its characteristics. When it's combined in just one single control loop, all the proportional, integral, derivative controls complement each other to get the fastest zero as possible. As we can see in the image, there are three controls in just one loop. We can see the integral, the proportional, and the derivative. Then it's the process, it makes the loop, and it tries to get to the set point and a zero error. The integral term improves accuracy, and the derivative reduces the overshoot from transient offsets. And the output of this kind of control can control valve positions, temperature, flow metering equipment, and a lot more things. So this was our presentation. Thanks for watching us, and I hope we got a 10. Thank you.